In this video, the product autonomous car will be analyzed and discussed from system engineering point of view, which include 3 stages. And for midterm report, I will mainly focus on concept development stage. Here are 3 parts related to the product: the background, concept development stage, and system engineering challenges. Autonomous car is an intelligent system built with computer as the center, which gives the vehicle the ability to get road, pedestrian, and indicator information to perceive environment, plan driving, and automatically control the speed and direction according to the obtained information. From other words, self-driving car is a simple-wheeled robot, which can simulate human driving through the dynamic analysis of surrounding obstacles and analysis of road conditions. All the controls and instructions are given by this computer. Driverless cars use their own hardware to sense road conditions and then control the vehicle to react after calculation. The ultimate goal of driverless car is to realize real driverless driving. Currently, autonomous car can be divided into 2 types. First, the vehicle itself is onboard laser reader, inertial gyroscope, reader, and any other sensor to sense the vehicle's road condition and surroundings, which is processed by computer and executed by driving system. And the second is the car is related to the Internet of Vehicles, which belongs to the category of intelligent transportation. Autonomous car integrates the science and technology in various fields such as automatic driving, intelligent computing, and artificial intelligence. It reflects the scientific and technological development and technical level of the country and has a broad development prospect in the field of nation defense and military and nation economy. With the rapid development of Internet and artificial intelligence like big data and cloud computing, the performance of autonomous car will be further improved. Compared with traditional car, self-driving car has the following new features: real-time navigation, global positioning system, high-speed planning and control, traffic sign visual perception, and dynamic obstacle avoidance. The detailed specification of highly automatic driving system and predecessor system, assisted driving system, will be discussed through system life cycle in following sections. The predecessor system, assistance driving system, featured with single-function auxiliaries such as anti-lock, constant speed, etc., but human resource is needed. Currently, advanced assisted driving system is popular and has been used in social life. Compared with DAI system, a DAI system adds functions such as adaptive cruise, emergency braking, and path deviation warning. The highly automated driving system has changed a lot from previous 2 stages. Cars equipped with HAD system will be able to drive themselves under specific conditions such as special parts on highway. According to analysis above, the successor system, the highly automated driving system, would be designed to provide perfect navigation, accurate positioning, good sense of surroundings, traffic sign recognition, and dynamic obstacle avoidance. For navigation approaches, there are 2 ways which is widely used now. The first is differential GPS positioning system. Through satellites to locate the car at different locations and send data information back to the base station on the ground and track the car's location for correction. It can avoid noise interference and errors, and the result can reach centimeter level. But like high-rise buildings, tunnels, and any other things can block GPS signals, and the cars will easily deviate from the right direction. So other sensing systems are needed to assist. And the second is inertial sensors. They detect and measure acceleration, tilt, impact, vibration, rotation, and multi-degree of freedom motion. After calculating and integrating inertial sensor data, the vehicle information can be obtained in real time, but the inertial sensor itself has the problem of deviation and noise. For machine vision system, engineers equipped the vehicle by long-distance camera on both sides of front and short-range radar on four corners of the car, which assists the vehicle take a close look at the car's surroundings. Short-range radar can quickly detect the moving things around the vehicle and avoid traffic accidents. Camera in front windshield is for identifying traffic signs, and camera in the rear windshield captures street scenes and determines the precise position of vehicle by comparing and distinguishing with terrain in navigation. For operational validation criteria, a positioning system that GPS-based positioning minded should be able to reduce external signal interference and able to deal with all kinds of emergencies to achieve more accurate results. And for traffic identification system, the traffic signal information should be accurately obtained by the camera with high resolution in real time, and the control center should rapidly detect the feedback to make the right decision. At the beginning of concept exploration, operational objects are restated. Instead, we need perfect navigation systems to ensure cars drive to the right direction. Cloud computing, big data, and other technologies are used to monitor climate data and road conditions in real time, so that cars should make the most time-saving, convenient, and safe road planning during driving. Accurate positioning system to park exactly where drivers want. Most GPS sensors are greatly affected by environment, and to some extent, inertial positioning can reduce environmental impact, and integrate GPS and inertial sensor data can greatly reduce the error. Traffic condition observation with the assistance of camera and short-range radar around the car in complicated road conditions. The radar should quickly detect the moving things around the vehicle and avoid traffic accidents and determine the precise location of vehicles. Traffic sign recognition captured by the camera will meet a different type of traffic sign, which means it should be able to identify both graphic signal and arrowhead signal by taking photos with the camera and output precise result. Dynamic obstacle avoidance with LiDAR will meet both stationary and moving obstacles. It's the key to the obstacles of path traveling. Radar not only need to realize static road environment problem, but real-time tracking the path of obstacles. At present, the accuracy of a GPS system can reach less than 5 meters. In the practical application process, the sensor combination technology based on Kalman filter mostly used to integrate GPS and inertial sensor data to achieve better positioning accuracy. In addition, some companies also use laser point cloud and high precision map matching, visual distance calculation to correct each other. Also, ultrasonic sensor convert ultrasonic signal into other energy signals with high frequency, short wavelengths, small diffraction phenomenon. Strong penetration of liquid and solid can help vehicle detect the external environment and make an appropriate response. Ultrasonic sensors are used in vehicle brake assist system and reversing radar to detect obstacles and avoid collision and friction. So the best way is to combine all the positioning minded to position vehicles. Currently, most obstacle avoidance sensors are laser radar, microwave radar, vision, and ultrasonic sensors. Laser sensing and microwave sensing technology uses radar to transmit laser and microwave to around target objects and then receive signal reflected from objects. Vision sensing system is based on image sensor. According to different intensity of current intensity, current signal in the image sensor driving voltage analog signals to complete the digital image. More recently, Internet of Vehicles technologies such as Zigbee and RFID technologies have realized obstacle information sharing. To the analyze about concept exploration stage, for performance requirements validation, we can conclude that multi-sensor combination of camera, millimeter wave reader, and ultrasonic reader suitable for automatic logic guidance in airports, factory, and workshops. The combination of laser reader, microwave reader, vision, and ultrasonic sensor will assist to build up a round dynamic obstacle avoidance system. GPS positioning is suitable for relatively safe and stable environment, and inertial positioning is suitable for local shot time positioning or auxiliary positioning. From what we have discussed above, we can find that for differential GPS positioning system is greatly affected by the environment, and the inertial sensor itself has a problem of large deviation and noise. Therefore, the integration of GPS and the inertial sensor data based on common feature will have high positioning accuracy, avoid noise interference and error in positioning, and when fast-moving vehicle position can be accurately calculated. For a better driving experience, single use of sensors and cameras will lead to the amount of data error, and high price later will increase the funding, which is not easy to put autonomous car into the market. At present, automatic driving environment perception mainly include two methods, the visual and lidar domains. One is multi-sensor combination of camera, millimeter wave reader, ultrasonic reader represented by Tesla. The second is the multi-sensor combination of low-cost lidar, millimeter wave reader, ultrasonic sensor, and camera represented by Google Waymo. So multi-sensor combination will have low cost and less error, and the receiving information will include more light and texture information. So we'll find the major changes over the predecessor system are navigation and positioning method. And the regular changes for every generation is a CD camera, 3D camera, millimeter wave reader, and ultrasonic sensor. Here are the diagrams show that those components with bold and underline involve major changes over the predecessor system, and the other components either retain the same features of predecessor system or have small changes. Although companies have made great progress in the field of artificial intelligence and put into the research of autonomous car, there are still some big challenges for further development. One is the sensor combination. Driverless car installed with HD camera and ultrasonic sensor were extremely easy to be disturbed due to some strong light noise and acoustic absorption material. This limits helped obtained a clear and complete image and make it hard to accurately measure the actual distance of obstacles. In addition, the accuracy of these devices decreases dramatically in extreme weather conditions such as high wind, fog, rainstorm, and the perception effect of reader and camera is easily affected, and the recognition of traffic lights will be affected correspondingly because the color saturation is different from that in sunny days. Therefore, information integration should be realized through multi-sensor cooperation, which is beneficial to assist automobiles' decision-making. Also, the cost. Hardware and software of self-driving car require huge environmental research and development funds for self-driving technology research. Since lidar is too expensive for mass production, the sensors in the autonomous driving system are many millimeter wave sensor and cameras. For example, the most expensive device in Google's driverless car is the laser rangefinder, which costs about 70,000 each, or more than half of the cost of Google's driverless car. The high cost is not conducive to the widespread adoption of driverless car in common life. And the safety. Driverless cars are connected to the internet, which expose the car to network security problems and increase the cost of building reliable firewalls. If a driverless car is infiltrated through the internet by cyber hackers, it can be controlled remotely, which may deliberately cause a safety accident. So that's all for midterm report. Thank you very much.